Yeah, today we're going to be talking about the FlightTracker, FlightTracker paper, consistency across read-optimized online stores at Facebook. Yes, this FlightTracker paper, it talks about something called read-you-write consistency, right? So right away, the first thing that I want to say is that we are not really talking about strongly consistent systems or even causal consistent systems. This is about this specific read-you-write kind of abstraction where the clients should observe their own writes. So it's a pretty weak consistency, right? It's very close to this eventual model with just like a little bit of a restriction about how eventual certain things can be. Right, so let's talk about this read-you-write consistency first. So if we have Alice, as the user, right, and if she writes, let's say this object X, she sets the value to 5 to some prior version of the object, right? So the data store has X to be 4. So if she writes it, once the write is acknowledged to Alice, if she tries to read it, Alice is expecting to get her own version, right? So this is kind of like very intuitive, right? If you wrote something, you expect to get the same. Now sometimes Alice can write something, and maybe some other user is going to write like right after Alice on the same object, and in that case, Alice will see even newer version of the object. And this is still fine with this read-you-write consistency, right? So, it's kind of assumed that the newer version, newer object superseded the Alice's write. So this X equal to 6 is even newer than original Alice's X equal to 5. So when Alice reads it, she kind of observes her write, which was overwritten by even newer write. And again, like this is very intuitive and very simple when we have just a single, copy of the data, for example, right? Single server in our data management application, in our data store. But what happens if we have more than one copy, right? So most of the applications, most of the storage systems, they are not single copy for redundancy reasons. So we have multiple copies and we have replication going on. So if Alice, writes this X equals to 5 to this replicated store, she will talk to one of the servers, and this server will apply her command, and that server may start replication. And sometimes, depending on the store, this replication is asynchronous or partially asynchronous, right? So we may have a situation where this write X equal to 5 was applied to the original server, original replica that Alice has contacted, and maybe it was applied to another replica, but it was still in transit to some other server. Now, from the Alice's perspective, the write has completed. So when she reads it next time, if she goes and picks a random server, if she reads just from one server, and she is not lucky and picks that stale server that hasn't received the update yet, then she will get the old value of the data. So this is clearly the violation of read-you-write consistency. And yeah, as I was mentioned in this in our little paper pre-discussion, if you're the user, this may actually freak you out. Like if you posted something, if you on Facebook, right, and then you refresh the page and you don't see your post, then you will wonder, okay, what did just happen? Did I actually press the button? Was it saved? Was it not? Why I don't see it? So it's kind of important for the usability, for the user friendliness of the application to be able to preserve this read-you-write consistency and not allow this kind of violations. So the question is then, how do we do it in this kind of systems where we can read from, let's say, a single stale replica, or maybe read from some cache? Well, the more traditional way would be to keep track of the versions for our data, right? So if we have this object X4 at version 1, when Alice writes it, she writes the x, x to be 5. When the write is completed, she will receive the new version along with her acknowledgement. So at this point, the Alice will know that the object X is at version 2, right? So this version 2 is, in a sense, a recency token that she can use on the consecutive read operations. So if she tries to read X and she passes along this recency token of version equals to 2, so she passes it to this stale server. The stale one is still at version equal to 1. And then the server can do the check and compare the versions in the token that Alice has and its own version. And it will actually not serve the read operation if it's stale, like if it's not up to date enough with what Alice is expecting. So instead of returning the stale data, this server can return an error, or it can maybe go and try to fetch the correct value from a different replica. So there are different mechanisms that we can employ to address the situation. But most importantly is we're not going to serve the stale data, right? So this recency token is the mechanism that prevents us from serving the stale data. Well, of course, in most systems, we don't typically have just one object, right? So in case of the Facebook, they talk about making possibly hundreds of requests against their Tau store upon each page render. So this 1,000 requests, they're not going to touch one object. They're going to touch hundreds of different objects potentially. So the naive way, and it will depend on how we implement the underlying data stores. But one way to deal with this multiple objects is to keep track of the versions of each independent object. So maybe initially we have X at version 1, Y at version 4, Z at version 7, and then Alice is writing another update to X. And when this update succeeds, the version is bumped up from 1 to 2. So now we have X at version 2, and the other objects still stored in this data store, they remain at their old versions because they haven't been written yet. Now, at this point, Alice can keep track of the recency token on a per object basis as well. So she knows that X was written at version 2. Now, if later she writes Y, object Y, maybe she sets it to some value 42, and obviously the version of Y is going to get updated in a data store. Data store will reply with this updated version, and now Alice can keep track of the Y at version 5. So she knows that these are her writes, and this is this recency information that she can use upon reading. So for example, if she needs to read value X at some point later, she can pass that X at version 2 to whatever the data store that she is going to be read from to ensure that the data store doesn't return the stale data, just like an example on the previous slide. So any questions so far? Obviously, this kind of approach has a downside, actually, because now Alice has to keep track. She has to keep track of all the objects she has written and their versions. So this recency token, it becomes quite large, right? So she either needs to transfer it, this large object all the time, or maybe somehow do the filtering when she reads so that she doesn't transfer irrelevant subtokens, right? Information about irrelevant objects when she tries to read something. So the downside is this increased storage requirement and possibly increased processing requirement to manage these large recency tokens that keep track of all the write operations.
So one question over here related to this only. If this log at the client side becomes big, and some entries are purged, so for those entries, if she issues new reads, she might not know the version number.
Well,
So how?
Exactly. So in my case, in my simple example, right, as I said, I'm doing like this gross oversimplification, at least so far, of what the Facebook is doing. You cannot really purge anything because, like, if you purge stuff, essentially you forget what you wrote. So this recency token is pretty much only growing. So that's kind of another problem of having these versions being set on a per object basis. Right, but this is nothing new, actually. Like, so, this is the approach that some existing systems would take, with some changes here and there. But to solve this inefficiency, what many systems do is they keep track of some global progress or global version, or at least the per partition version of the object, or not of the object, but of the entire data store. So consider an example where we have a data store that still has the X, Y, and Z objects, but now it has this logical sequence number that is common for the entire data store instead of per object. So when Alice writes X to this data store, the sequence number is going to get incremented and returned back to Alice. So now she knows that her latest write was happening at sequence number at 6. Now, if she does another write on a different object, let's say object Y, she updates this object Y, she gets the feedback that, okay, the sequence number has moved up to 7. So because this is this partition-wide global progress tracker, right, progress marker. So now her token is essentially just one number instead of the token that consists of all the writes that she has ever done. It's always one number, which is a lot more compact, right? So it doesn't have this problem of ever growing, and doesn't need any explicit compaction mechanisms. It's already compact. It's just one number, 64-bit integer, for example.
Quick question here. So is this for just this particular user? Because if there are too many objects, then this number is going to keep changing very quickly.
So this number is the number here on the right side is per database, per partition. So it's one number in the entire entire database partition. So the user has her own marker, right? The token is 6. The database can go up much further. Maybe some other user is writing and now it's going to 8, 9, 10, 11, and so forth. But Alice is still knowing that, okay, her most recent interaction with the database was at the progress number 7. Right, so this number is just one number for the entire database, and Alice is only keeping track of the latest interaction with the database.
I think we assume that the LSN is in sync in all the replicas.
So yes, obviously in this kind of scenario, right? As I said, it's a global version, right? Global progress tracker. So this would be maybe like a database that has a leader who can assign the sequence numbers and then do this asynchronous replication. Alternatively, this may be some kind of synchronized time, like a hybrid logical clock, for instance. This approach is, for example, used by MongoDB, right? So MongoDB, they have a hybrid logical clock, which is a synchronized time, and they use this, hybrid logical clock as the progress marker. So instead of like a version number, it's like a little bit more loose progress marker, and this allows them to do, essentially, to have this recency token that's just one number, a timestamp. But yeah, you're right. This requires you to have some kind of a central authority in the database that at least assigns these numbers, or to have this synchronized time like HLC, or both. So
is it like storing like a historical snapshot of all this information on the server side?
No historical snapshots on server side. So when Alice wants to read something at 7, she knows that something at 7. The database at this point may be at 100 because of other interactions. And that's totally fine, because remember, she wants to read her own write. So if the database moves forward, it's fine. Like, she doesn't need to read the state at 7. She can read the state at 100, because that state at 100 will encompass her operation that she did at 7.
Okay.
Right. So there is no need to keep track of snapshots. Like, you don't do anything expensive. You just keep moving. The database, the data store just keeps moving. The only reason why we have this is that if Alice decides to read, for let's say Y operation, and she goes to a stale replica, the stale replica will recognize that, okay, it's not at 7 yet, so need to do something else, like retry or try a different replica, or wait for the synchronization to happen. So this is like a very low overhead, lower bound recency token. So everything above 7 is going to be fine for Alice at this point. So this, however, also has a problem. So the problems will start to come in the Facebook case, actually, right? So if we have a little bit more complicated system that maybe has a persistent store and has a cache in front of it, right? So the cache, for one, it will not have all the possible data, right? So it may have some entries missing. For two, it will be too expensive to keep the cache synchronized with the database on all the objects perfectly. So while the database may be, for example, at LSN 6 after Alice has wrote this x equal to 5, the cache may be at the previous version. So the cache version may be still like x. The version of x maybe was read, was placed in cache at LSN 2, and version of z maybe was placed in the cache at LSN 5, right? So cache is inherently stale, and it doesn't synchronize as much, and it doesn't have all the data. So if Alice keeps writing, she like, once again, wrote her Y42 operation, bumped up the LSN, the sequence number, to 7. She has this recency token at 7, and now she wants to read something, right? So remember, the first operation we did was x to 5, x set to 5. The second operation is y set to 42. Now Alice wants to read x. If she reads x, her recency token is 7. She goes through the cache. The cache has x, right? So it's not like a complete cache miss. The cache has x, but it has the x that was retrieved at number 2. So from the cache's perspective, this is old, right? So Alice wants something that was at the global version 7, but this cache was at the value of x at version 2. So Facebook calls this consistency miss. So it's not like a complete miss of the cache, but it's missed because of this token value. So what happens, like in this example, I have a read-through cache. So in this case, the cache server will reach out to the database and retrieve, right here, it will retrieve the x equals to 5 value at the latest LSN, update the cache, and then the cache return back to the client. So this actually worked as expected, right? The cache was stale. Alice was expecting to get her write of x, so the cache had to be essentially refreshed. This worked as expected. However, if Alice wants to read z, and remember, she didn't write z, so she never wrote z. If Alice wants to read z, our consistency token is still at 7, and the cache thinks that z, like the cache's z value is at 5. So from a read-you-write perspective, it's perfectly fine to return 5, right? Because Alice has never wrote z. But because our our consistency token, our recency token is at 7, it's it kind of overshoots the z. So this will actually cause another cache miss, consistency miss, and require the cache to go back to the store, retrieve the value of z, and return z back to Alice. So this is something that we could have avoided if we had more information, right? If we did keep track of all the versions for all the writes that Alice did, then we could have said that, okay, Z had no expectations of recency, so give me any Z you have. That will be absolutely fine in terms of enforcing read your write consistency. And because of this, because we tried to shrink our consistency token, not consistency, recency token, right? Because we shrank this recency token to just one number. Now we are doing extra work. So guess which approach Facebook is using? So in the FlightTracker, they do the per version tracking of objects, right? So again, and this is kind of the big selling point that they have. They call the recency token, they call it a ticket, and they ensure that as Alice keeps writing, her writes are recorded in this ticket, right? So the ticket will record, okay, Alice wrote X at version 2, then Alice writes something else, like writes Y, it will record that Y was written at version 5, then she writes Z, and the ticket will again be updated to reflect this information, right? So the reason that Facebook is doing this is purely because this is more efficient for their highly cached system, right? So if we actually look at how Tau social graph system works, it tries to serve pretty much everything from the cache. So having cache misses because of reasons that they can avoid will actually slow down the system. Whew. So yeah, this is what Facebook is using. But as we saw before, right, this consistency token will keep growing forever unless we do something. This recency token, I keep saying consistency. So what Facebook is doing is they call compactions. So one simplest way of compaction is essentially keeping track of only one, only the most recent write for a particular object, right? So if Alice wrote X, she set it to 5 at first, it was version 2, then she did some other write, and then she writes X again and sets a different value. Now we no longer need to keep track of the version 2 write for X because it was superseded by the version 3 write for X. So that's like the basic, the most trivial way of compaction. They call it compaction. I really call it common sense. But this is one way. We can get rid of unneeded entries in the recency token in a ticket. I should start using Facebook term ticket. The second type of compaction is this cross-scope compaction. Right, so and cross-scope compaction is, let's say, you actually have the system that has this LSN numbers, right? Sequence numbers or transaction numbers, some global or at least per partition way of keeping track of progress. So, as Alice keeps writing, maybe she wrote X at some version, it was at 5. She wrote Y at version 6. She wrote Z at version 7. If she has too many of these objects, at some point it may become more cumbersome to keep track of this big ticket instead of just keeping track of this one LSN number, right? So in this cross-scope compaction, in a sense, what they do is they say, okay, the burden of per write tracking is too much. How about we replace all of this write with some global version tracking, right? So instead of per object, now we're just going to say partition A, this particular database is at LSN 7. This will cause more cache consistency misses, as we saw in my little toy example. but it does help keep track, keep the ticket size under control. And the paper is explicit that they don't really do this that much, that often, because obviously it reduces the efficiency of the caching systems. And finally, they have this global compaction, which is really the artifact of, which is really because of how the system, the caching, how the tau works itself, right? So they say that they're so confident that whatever the write that has been written by any user, that this write will replicate through the data store within 60 seconds. They're confident that either all the data stores and the caches will get updated with this write in 60 seconds, or the caches will just drop that key in 60 seconds, so that it's going to be a cache miss that goes to the store. So because of this 60 seconds confidence that they have, they say that we're going to prune any write information that is 60 seconds old, right? So at any point of time, at no point of time, the ticket has the writes that are more than 60 seconds old. Like if the ticket has this write, it will be removed to keep the ticket size under control. This is how this ticket system as a recency token works. Again, very high level. Let's put this in a big picture, right? So from the user perspective, we have our lovely browser. The user is interacting with Facebook via the browser, and maybe the user wants to load the page. This page load request will go to some web server, right? Obviously, it will go through some load balancing to pick the web server, but eventually it will end up to this web server. And the web servers, they actually tend to be sticky in Facebook, so that next time the user is likely to go to the same web server, or at least the same web server group. So the web server is then going to get the ticket information from the FlightTracker. So essentially, the first thing that the web server is going to do before fetching all of the information to compile the page is going to get the ticket associated with this particular user ID. So it goes to the FlightTracker, asks for the ticket for the user ID, and it will receive the ticket back. Now it can use this ticket to perform the reads, reads and writes actually. So it will include this ticket in every operation it's going to do against the data stores, the caches and the actual persistent data stores. And once all of this information is collected, obviously the web server can compile the web page and return back to your lovely browser. So this kind of covers the read path. In case the request, in case whatever the user is trying to do includes a write, then there is an additional step, right? So in addition to requesting the ticket, once you have the ticket and you start performing writes, because you performed the writes, you need to update the ticket, right? So maybe you changed some object that was in your ticket before, or maybe you wrote to a new object. The point is you need to update the ticket. So on every time there is a write involved in this end-to-end scenario, then before returning the page to the browser, essentially the ticket is going to be updated in the FlightTracker, right? So we're going to include all of these additional writes in the ticket and save it in the FlightTracker. And only after everything is okay, we can proceed. And the FlightTracker service itself is purely in memory, and it's a simple hash ring kind of approach. So if you read the Dynamo paper, this is a Dynamo probably even more simplified. So they do enforce the read and write quorum intersection, so that whatever so if that write has actually succeeded, it will be read the next time. But if the ticket write, so here we're talking about the ticket write, right? If the ticket write has not succeeded on all of the nodes, it's fine to return the bad data, because unless it succeeds, the user is not going to see it anyway, like the result of this operation. So this this is a very simple system actually, and they deploy it locally in every data center, and or keep all of these quorums in a data center. So the FlightTracker rarely spans multiple data centers. So there is like a separate instance of FlightTracker in each data center. And yeah, the paper doesn't really talk too much about the performance, but there are a few interesting performance metrics that they have, like the read response. The average size of a read response from the FlightTracker is 250 bytes, which means that the average ticket is about 250 bytes. So it's not big, and the median ticket is actually 0 bytes. So that means that a lot of the compaction, the 60-second compaction works pretty well and gets rid of all this data. So for a lot of the use cases, like if you're not like frantically keeping pressing on F5 button or like liking everyone every few seconds, this ticket size is going to be 0. And a little bit on the FlightTracker performance, because it is involved in every user request, essentially, right? Like when the user is doing something, the FlightTracker will be involved potentially, right? At least to get the ticket and maybe to write the ticket back. It needs to be very quick. So for the quickness, they say it's 288 microseconds. So 1/3 of a millisecond for reads and a little bit more than 1/3 of a millisecond for writes. So pretty fast on average. Yeah, that's all I have. That's my half-an-hour presentation.